Welcome to a system-wide analysis of the brain's hidden ecosystem. Today, we are exploring the glial consortium. We will reconstruct the chronological cascade of neurodegeneration, fundamentally changing how we view cognitive decline. For decades, neuroscience has been trapped in a neuron-centric illusion. Historically, pathology focused on two things: the victim, which is the dead neuron, and the tombstone, which is the protein plaque left behind. This outdated model assumed cell-autonomous failure, completely ignoring the complex cellular ecosystem surrounding it. As the saying goes, we mistook the debris of the battle for the cause of the war. To understand the war, we have to look at the missing decades. We used to think of the timeline starting when clinical symptoms appear, but neuronal death is actually a terminal event. There is a silent cascade that occurs over the 20 to 30 years prior. Robust inflammatory and metabolic signatures precede overt neuronal loss by decades. Current therapies fail precisely because they target this terminal phase instead of the silent onset. The brain is an obligate immunometabolic syncytium, a highly interdependent network. Neurons cannot dilute damage through cell division. Instead, they rely entirely on a glial consortium for waste clearance and energy. This includes microglia, acting as the sensor and immune vanguard, Astrocytes, the gatekeepers and transmitophagy engines, and oligodendrocytes, the sustainers, providing metabolic fuel. When this consortium fails, the neuron dies. Let's wind the clock back 20 years before the first symptom. This is phase 1, the invisible injury. Here we see an internal cellular plumbing failure. Before the surrounding support cells revolt, the endosomal lysosomal pathways inside the cell jam. The cell is technically alive, but its recycling centers are broken. In Alzheimer's disease, this manifests as an endosomal traffic jam. Driven by APP-CTF, there is a hyperactivation of RAB5. This leads to a hyperacidification failure. The VATPase proton pumps are inhibited, and the lysosomal pH rises above 6.0. As a result, the lysosome becomes a toxic storage dump. The consequence? Nerve growth factor transport is blocked, and the neuron begins to starve. Around 15 to 20 years pre-symptom, we see similar ecosystem failures in other diseases. In Huntington's, we see an oligodendrocyte arrest. Mutant Huntington prevents the maturation of oligodendrocyte precursor cells. This leads to impaired axonal support and decompacted myelin layers. Ultimately, the failure of the MCT1 lactate shuttle causes metabolic starvation. The neurons are starved of energy by the very cells meant to support them. Moving to 10 years out, the prodromal phase, this is phase 2, the glial revolt. Glial cells are initially protective, existing in disease-associated or M2 states, where they clear debris and support neurons. But chronic stress drives them from protection to toxicity. They enter states of senescence and hostility. At 5 years out, chronic stress takes its toll. Microglia transition from a protective disease-associated or DAM to a senescence-associated or SAM. Chronic exposure to A-beta for more than 24 hours causes lysosomal damage. The cell stops eating waste and instead releases inflammatory cytokines, which actively paralyze neuronal autophagy. In ALS, the betrayal is even more direct. Astrocytes become the executioners. Protective astrocytes undergo a phenotypic shift into aberrant astrocytes. Through the secretion of trail, they trigger a suicide sequence in the motor neuron via death receptors and caspase-8 activation. It is friendly fire. The support cell executes the neuron. At 5 years out, early functional deficits appear in phase 3, the synaptic collapse. The network goes dark. The synapse is the vanguard of functional loss. Cognitive decline begins here, not with cell death. The cells are physically present, but the lights are going out. In Parkinson's, synaptic failure occurs 10 to 20 years pre-onset. Motor signs only appear after roughly 30% of neurons are already dead, suffering from retrograde degeneration and alpha-synuclein aggregation, but the network failed years prior. In multiple sclerosis, we see a pruning error. Vivid coral microglia mistake healthy synapses for debris and prune them away via C3 complement activation. Glial glutamate transporters are inhibited, severing connections, leading to synaptic loss completely independent of demyelination. Finally, we reach clinical onset, year 0. This is the terminal event. We see panthos and cellular lysis. The neuron suffers lysosomal membrane permeability. The extracellular plaque we've studied for so long is not the killer. It is merely the tombstone of a neuron that died of constipation. When we grade the cellular drivers by causal relevance from 1 to 5, the data is clear. In Alzheimer's, Parkinson's, ALS, MS, and Huntington's, synapses and microglia consistently rate the highest. Glial dysfunction acts as the primary initiator, a grade 5 threat. The neuronal soma is merely the terminal victim, a grade 1 outcome. This demands we rewrite the therapeutic playbook. The old strategy focused on clearing tombstones, which consistently resulted in late-stage failure. The new strategy must focus on restoring metabolism. We need to target lysosomal acidification and glial coupling. We must intervene in the silent decades. To summarize the chronological cascade, at -20 years, we see broken endosomes, endolysosomal dysfunction, and cargo accumulation. This is molecular failure. At -10 years, angry microglia drive chronic activation and inflammatory signaling. This is glial exhaustion. At -5 years, we see disconnected nodes, circuit disruption, and synaptic loss. This is synaptic silence. And at year 0, symptom arrives alongside tombstones, neurodegeneration, and neuronal death. The crucial takeaway? The window opens 20 years before the first symptom. Thank you for joining us in this system-wide analysis. The path forward is clear. We must treat the ecosystem, not just the neuron.